Hello, welcome to the last segment of my alum video. Part 3, the roundup of the alum. As you can see, there have been many changes to my alum crystals since my last video. In the last video, the only thing visible in my vial was a fuzzy looking blob floating in the middle. Now, actual crystals are visible on the bottom and on the sides. The crystals are clear and fairly large, and there are too many of them to count individually. They are shaped like little round crystal rocks. There have been no drastic environmental changes to my crystals since my last video because it has remained unmoved in my dorm room. If anything, however, the increased amount of sunlight in my room and the open window on the recent nice days have caused a slight increase in my dorm's room temperature and humidity. These factors could affect the evaporation rate of the solution. If I wanted to grow one giant, high-quality, single crystal of alum, I would have to use something called a seed crystal. Basically, this is the act of putting an already formed solid alum crystal into the saturated solution in order to designate a site of nucleation. This time, rather than allowing the alum crystals to grow individually and allowing the growths to compete with each other, as we did in our first experiment, now all the crystals will conglomerate onto the seed crystal, and the seed crystal will become the site of our single giant high-quality crystal of alum, right here. Moving on, in a crystalline structure, the atoms are lined in such a way that they create many repeating parallel planes. As you can see here, the atoms are drawn as circles, and the parallelograms show the parallel planes they create. D-spacing essentially defines the amount of space between the atoms in a crystalline structure, or the amount of space between these parallel lines. D-spacing is shown here. If the d-spacing is said to be large, this means that the atoms in the crystalline structure are spaced far apart. The structure would be less dense. If the d-spacing is said to be smaller, however, then this means that the atoms are packed closer together with less distance between each of the parallel planes. The structure would therefore be more dense. When we know the d-spacing and the angles between the parallel planes, we can understand a lot about how the crystalline structure was formed. Bragg's law is the formula used to determine the quantity d, representing the d-space, of a crystalline structure. Bragg's law is shown here. 2d sine theta equals n wavelength. Because X-rays have the perfect wavelength for diffracting off a structure's parallel planes, X-rays are used to determine d with Bragg's formula. In the equation here, 0.15418 nanometers is the wavelength of the X-ray used. We got this by looking at the intensity versus 2 theta graph that we were told to look at. In the top right-hand corner, it gives us the wavelength of the X-rays. In addition, in our equation, we use n is equal to 1 because, again, in the graph that we are looking at, we are trying to find the d-spacing of the highest peak. N should be equal to 1, or higher integers for n would correspond to lower peaks. So thus, because we are using the highest peak, we should use n equals 1. Because the intensity versus 2 theta plot uses 2 theta as the x-axis, we should divide the value of 21 degrees by 2 to find theta. So here's our 2 theta, 21. We divide that by 2 to find theta is equal to 10.5. At last, we can plug everything into the Bragg's formula to determine that our d-spacing value is 0.423 nanometers. This represents the distance between the parallel planes of atoms in the given crystalline structure. Well, now that we've covered a bit about d-spacing and Bragg's law, that concludes my alum crystal series. Thanks for watching.